So this talk is actually happening against all odds. Fate definitely did not want me to come here, thanks to United Airlines. So last night, I was supposed to get here like midnight, and obviously there's a mechanical failure. They put us on the tarmac. They're a couple hours on the runway, and then they get us back to the gate, and then they were going to switch me over to a different plane, but consequently, San Diego apparently had a curfew because there was some construction going on. So they diverted us to LA, and then we got out of the airport in LA just like in the wee hours, like looking for buses to shuttle us here, and like we keep waiting, and then we keep waiting, and they never arrive. And then finally they arrived, and then it takes like a few hours to get here. So anyway. There's only 1 or 2 days that I'm on coffee in a given year, and today is one of those days. So apologies ahead of time. If anything is unclear, if I skip over to go too quickly, just let me know. I'm happy to pause. So awesome. So let's see. So you're here in the talk, the new era of software-enabled manufacturing. So I'm Shashank. I'm a co-founder at Tempo. Anyone heard of Tempo here? Awesome, familiar faces. Awesome. So we call ourselves the world's fastest electronics manufacturer, based in San Francisco. So people ask me, why do you have a factory in the middle of San Francisco, next to software companies paying San Francisco rent? And so first off, you're not building 1 million iPhones. We're not Foxconn. So what we are building is, we're building prototype and low volume production quantities of very, very high complex designs. Boards that go into rockets, satellites, medical devices, etc. So secondly, I think we are there because we think there's a fundamental mismatch between the pace at which customers are moving and pace at which traditionally manufacturers have moved. It's really light and day. And that's the whole reason we came over from being a customer to the manufacturing side. And so the entire industry leaves a lot to be desired. So we're in the middle of SF because we're competing for the same engineering talent as our customers are. That the thing that drives our customers also drive us. We were talking about lean product development early on. That's what internally for engineering, that's what drives us as well. And obviously we're trying to offer that to our customers. So that's us. But what I wanted to talk about today is something called continuous manufacturing. So at Tempo, we are always thinking about how to make electronics development more like software development. So what I'm going to focus on is why we think continuous manufacturing, as we define it, can deliver a future of launching products faster, with greater confidence and with greater precision. So let's first, before we go into that, let's first talk about traditional contract manufacturing. So how we define this is, it's one that is especially optimized for mass volume production, right? It takes a lot of time and work to go from CAD design to having all the machines on the floor programmed. But that's okay because once you press start, you can make 1 million boards. You can amortize that to the millionth unit. But if you're only making a few boards for prototypes, or if you're making hundreds of boards for low volume production, it actually takes longer to set up the floor than the actual production. So, so when you're iterating a design, when you need to integrate changes to a design to a manufacturing process that's already underway, it can be very frustrating. Why? Because traditional manufacturing is fragmented. Sorry about the small text there. You have many people doing different parts of the process, sending emails, spreadsheets, and then when you walk into a floor, it looks something like this, where you have all these very intricate pieces of sophisticated technology, pick and place assembly machine, solder paste printers, automated optical inspection machines. All these are islands of activity. They're not talking to each other. They don't have a clear, a connected information flow. It has its own unique rules and formats and interfaces. It's everyone is all the machine vendors, all the supply chain vendors are doing their own thing, but they're not connected. They're not talking to each other, and it means a lot of. It could mean bad implications. Essentially what it does is for prototyping low volume production, the time it takes too long. Coding takes multiple days, production takes many more days, and debugging and rework and takes many more days. And essentially you come up with something that is incredibly slow, arduous, and lots of back and forth, and quality isn't great either. Because it's such a labor-dependent production. So anyway, so that's sort of contract manufacturing as we see it, and we talked about. You probably heard us talk about this type of thing in the past. But what we think is that contract manufacturing, as we know it, is done. It's broken. It's impeding innovation. It's not fast. It's not flexible, which I'll focus on today. It has limits to how closely a designer can actually partner with manufacturing. When I did my talk last year, exactly this time here, I talked about communication and partner, what a close partnership with manufacturing actually means. And I talked about the limits of how closely you can actually partner, especially for highly complex designs. So this needs to evolve. We need a new paradigm. And so before I go into continuous manufacturing, let me talk about the software development philosophy. Again, we're always talking about how can we make electronics development as fast as software. So let's see if we can get some inspiration from the software development side of things. So you guys have heard continuous integration and continuous delivery on the software side, right? So it's a very common pattern where developers integrate code into a shared repository with high frequency, and each check-in is verified by an automated build. And so it allows teams to detect problems early. On the continuous delivery side, it refers to the production of software that passes those automated tests. So essentially what you're able to do is you're able to make small continuous changes, test them, and deploy them to production very flexibly, right? Regardless of what the production state is, most of the time, you're able to push these small continuous changes. So that's what CI/CD is on software side. So and GitHub is an interesting product. So you guys have heard of GitHub? Most of awesome. So it's built on an open source tool called Git, and it's a distributed version control system and a code management system. And GitHub built a bunch of features on top for collaboration, issue tracking, change requests, pull requests, and has also many integrations for deployment. So 40 million people use it, 100 million projects hosted, it's massive scale. And software engineers, so why are we talking about this? Because software engineers collaborate on very highly complex software projects using GitHub, right? It's not a perfect analogy, but what's interesting is many of its collaboration and change management tools, I think, are very relevant to manufacturing. So taking that inspiration, let's talk about continuous manufacturing. So I think we need a new paradigm, a paradigm where engineers are so well tied to the factory digitally, one where engineers can push small changes to the factory that is automatically configurable, and one where design data and ideas flow into the factory and back into the design in a continuous digital thread, a thread that connects the design data directly to the machines on the floor, people on the floor, and the supply chain. So hopefully one where quality issues are rare and way more rare than today, and one where you can experiment ideas quickly. So anyway, so that's sort of the introduction. What I'm going to focus on is sort of two ways continuous manufacturing, I think, can really transform electronics development to make it more agile, to make it closer to that of experiencing developing software. So what do I mean by that? So I'm going to first talk about communicating ever-increasing design complexity while maintaining speed and quality. So designs are getting incredibly complex, right? And new materials, new fabrication processes, HDI, stacked microvias, complex assemblies, products that are getting very complex. But the need for speed and quality, though, hasn't changed. So what also hasn't changed is the communication pathways with the manufacturer, right? To relay the design intent. So this may be very familiar. I think sort of this is the state of the world as it looks today in our view, from a manufacturer's view. So you have, for communication channels, you have phone calls, emails. Some people have a website, text, right? Slack. And you have design data, which is also fragmented. You have ODB++, Gerbers, BOM, assembly instructions, stackups, right? You're sending all of these set of files, and you have fragmented stakeholders as well. You have a component engineer, design engineer, purchasing folks. Like all of them, each of them are accountable for their specific thing. And what you end up is you have intent that is scattered. And for highly complex designs, this is a massive problem. We build flight boards that go into rockets and jet planes and medical devices. So it's the reliability and regulatory requirements for these designs are incredibly high, and that margin of error is so low. Like you can take a rev des and reference designator, and if there's a small mistake, it has big implications on how the machines understand the BOM. Something that may seem as small as putting a wrong 2D label on the boards has big implications for traceability, right? So when the intent is scattered, you're introducing lots of chaos, and chaos increases exponentially. So going back to the software development analogy, let's see how GitHub sort of solves this problem on the software side. So this is GitHub, a screenshot of a change request by a collaborator. So here you have a collaborator submitting a change request for code, right? So collaborators, you have discussed the specifics of code that has changed before and after, right? When you look at this, it seems, of course, that's how it should be developed, right? But there's actually very interesting things, very interesting principles that you can pull out of it that are interesting for manufacturing. First, it's contextual, right? There's actually visual diff you can see for how the code has changed. And two, it's very collaborative, right? And three, it's persistent. You can always go back and see what communications led to a change. And four, I think most importantly, it's a unified and shared intent. So you're speaking the same language. And this is very important. I think on the software side, this is sort of granted, but a shared intent, like a shared understanding of the intent is very important. And so what does this mean for electronics manufacturing? So I think we should start with a unified shared intent. So let me ask you guys a question. So you see the picture of the same board here. So it's actually one of them is a tempo simulation of a fabrication, and the other one is the actual picture of the board after it's been fabricated. So one of them is a simulation that Tempo has built. One of them is a picture of the board. So maybe I can ask you guys a question. So which one do you guys think is the picture of the board? A, B. So who thinks it's A? Picture of the board is A, right? About half of you. Who thinks it's the B is the picture of the board? All right. Slightly higher than half. So the answer is the picture of the board is B. How did you find it?
You can identify the margins.
Oh, the margins.
The edge of the.
Oh, yeah. Cool.
Small.
Oh, interesting. Cool. You use the through holes. Oh, interesting. Cool. So, I'll explain to you how we got to A. So essentially what we did is we took that rich design data, so not Gerber's, and as well as a software understanding of the machine properties of our fabrication vendors, and some computer vision to come up with essentially a photorealistic version of what we're planning to build. So it's essentially it's a virtual representation of our understanding. So traditionally, there's big discrepancies between how you and the manufacturer interprets a design. So you guys are familiar with sending Gerbers over email, getting boards back. That's not what I meant. That's not what the CAD says, right? So it's very common here. Once you start with a simulation of exactly what it's going to look like, there's no guessing, right? It's what you see is what you get. So this allows our customers to find design issues and discrepancy issues before a build starts. But I think what's more interesting is it starts with a shared intent. Like you have the same understanding. And that seems so basic, but it hasn't happened till now. So what you can do once you start with the shared intent is you can overlay a collaboration. So same as GitHub, you can start with a shared visual understanding. You can overlay collaboration. So for example, after you submit the design, you can communicate with the DFM engineers on the manufacturer side and get feedback contextually on all kinds of issues. So instead of communicating over many different channels, emailing screenshots, spreadsheets, you know exactly what the intent is, you know exactly what the issue is. And so especially for highly complex designs, this type of context is incredibly important. So you can resolve issues quickly and precisely. Precisely is important. So we've been in the industry for so long that it's like there's such small things that can be discrepant between what the customer thinks we're changing and what's actually being changed. So this is a shared source of truth, and you can collaborate. You can. It's always persistent, right? You can always go back and see what the feedback was that led to a change. This is the fun part. So after you have this collaboration, what you can do is after you have that digital model, you can augment it with data collected from the factory in real time, right? So that's what continuous manufacturing can enable. So this, what you see is the boards going through pick and place and reflow. So pick and place assembly and reflow. And it's a picture of the first article board. So first article is essentially the first board that goes through the line to ensure that all the manufacturing specs are met. And you can tweak the manufacturing line depending on what issues you find. So this is the first article board as it's coming off of the factory in real time. So why is this important? After manufacturing starts, traditionally there's radio silence, right? With continuous manufacturing, you can see the boards as they're being produced. You're literally digitally there, right? For highly complex designs, and also for production boards, low-volume production boards, you don't want to wait till the boards get back to you to see issues. So this allows you to easily find issues way before they even get to you. So this type of communication has been super interesting for us. So continuous manufacturing can also do this. So once you have a digital thread that connects directly to the machines on the floor, you can take defects that, in this case, the automated optical inspection is finding, or really any defects that any human finds on the floor. And in real time, you're able to, as an engineer, you're seeing what those defects are as they're also being fixed on the floor. So the most important thing about this is it enables us to build the right thing. Like we want to build the right thing. Manufacturers want to build the right thing, and it's very hard. And here, just having the confidence that the customer is digitally there the whole time gives the manufacturer a lot of confidence. Because what we see is what you see, right? It's It's so simple. So you can do this with X-ray imagery as well. And you can do for fab inspection. You can do for a lot of data that the factory is collecting in real time. So there's this concept called a digital twin. Have you guys heard of the digital twin concept? Some of you. So it's kind of marketing lingo sometimes, but it has some sense to it. So essentially what a digital twin is, it's a virtual representation of a physical asset that exists simultaneously with the real physical entity, and there's a real-time connection between the physical asset and the digital model of it. So essentially, that's sort of that's what happens when you sort of in real time get this factory data. So essentially, you're building the digital twin as the boards are going through manufacturing. So the interesting thing about this is after the boards are deployed in the field, for example, you can always come back to it a year later and access the digital model that represented the actual fab, actual as-built product, and reference it. So in continuous manufacturing, this data should be persistent forever into the future, right? So say you deployed a satellite and you wanted to see exactly what version of files, what specific reflow profile, and what specific design format has been used, you can always come back and check. So for highly complex designs, again, this is a very powerful way for collaboration. So the second thing that this enables is frequent changes. So especially changes mid-build. So manufacturing process has already been set up, and you find something that you want to change, something that you want to improve, and you want to push it to the floor. Traditionally, who submitted engineering change orders here? All right, a lot of you. Who loves that experience? All right. So multiple people have to sign it, right? And for the changes to become effective, there's multiple days that go through for the changes to become effective. It makes sense because for highly complex designs, there's a lot of room for error, and it's a lot of CYS stuff, right? It's like you want to make sure you're only changing what's actually changed and not anything else. So what are the examples of changes that can happen mid-build? So BOM changes, right? Like you can DNP a specific revdes. You can do an MPN change. You can add new BOM lines. You can change quantities. Assembly instruction changes happens all the time. Customer says, as the boards are going through the factory, hey, we want to change the reflow profile. Conformal coding profile, right? Press fit installation changes, and these are changes that are coming in as the boards are flowing through, and functional testing changes, right? If you have an ICT flying probe, or you might say, hey, I found a better way I found an improved version of the solder paste geometry. I want to push it to the floor. I know 10 boards have already gone through, but I want it to be reflected in the next 20. So all kinds of different things could happen, but engineers don't do them. Manufacturers don't do them. They don't like it. Why? Well, this is actually so giving a manufacturer's view of what actually happens. So say you changed one BOM line, or say you DNP'd a part. What actually happens on our side is we have to understand exactly what the change was, which is hard, right? It's like when you're sending new versions of your BOM, new versions of your spreadsheet, right? It's not trivial to find exactly what the diff was. And then after we understood that change, you have to procure the parts. You have to update the parts checking program. Right? It's the expectation of what parts go into your assembly. You have to update the traveler. The traveler is a set of instructions that guide the technicians on the floor. So if you have a visualizer, which I was showing you earlier, you have to update it, which we use for QA. You have to update the component feeders that go into the pick-and-place machine. You have to update the solder paste geometry program or procure new stencil. You have to update the pick-and-place program, AOI program. There's probably things I'm missing here, depending on what the change is, but this is highly error-prone, right? If you're making if you literally DNP'd one part, you're introducing chaos on the floor. And there's ERP systems, there's off-the-shelf systems that help people do this, but fundamentally, because the information flow is fragmented, because all the machines don't talk to each other, this is incredibly manual today. And the industry is just full of fragmented technology, so you sort of have to do this very carefully. You have to have clear ECO forms, and so no one has tackled the unbroken data flow. So what does this mean on continuous manufacturing world? So actually, before I go into that, every time you make a change, the thing that also has to happen is we have to document the part level traceability. Everything that has changed, to who, when, version of customer files used, the process input files used, the materials used, QA approvals. All of this has to be documented. Manufacturers don't like this type of documentation. It's also error prone. It introduces machines are down, lines are down. And in effect, engineers are not able to push changes to the factory. So how do we flip this? How does continuous manufacturing look like? So if the experience was like software development, I think it looks like this. You would submit your changes and see what the change order impact was. So say you changed out an MPN mid-build, the software would see what stage the boards are at in the floor, understand what the changes need to be made, and present you with the options like this. So say you made 5 BOM lines edited with MPN changes. So say that was a change. You would understand that boards 4 to 6 cannot accept those changes because they're currently in final QA. So you can either accept that or you can request rework, right? So that's definitely an option. You can choose it, but it has a day impact or and some dollar impact. But for boards 7 to 50, it can be built with these new changes, and it has some time and cost implications, and you can just accept it, right? So that's a fairly simple change that you can make. There's more complicated ones you can do, but so that's sort of the vision of how the customer experience looks like, and this is the fun part. When you do make a change, and once you're approving those changes, in continuous manufacturing world, all those changes flow right through to the programs that run the floor, right? So the parts checking program, here's basically, all the parts come into, are delivered, consigned parts, parts from DigiKey, Mauser, et cetera. And this is an expectation of all the parts that we need before the assembly starts. So in this world, you submit the changes, this gets updated automatically. So there's no manual. And how about a pick and place program, right? This is a software that we use to program our pick and place machine. No manual intervention. Those changes should be propagated to the pick and place program. The digital traveler. So this is essentially a set of instructions. It's a dynamic set of steps that guide the technicians on the floor around building an order. In this world, this should be dynamically updated. And as an engineer, this kind of becomes quite beautiful, right? You can make all the changes you want, whenever you want, even for incredibly high reliability, highly complex boards. So, what does this all enable? Why does this all matter? So let me give you a story of something that happened to us earlier this year. So a major medical device company came to us, and they were about 6 months behind schedule, and they needed to produce about 1,000 of these highly mission-critical boards for these surgical systems that they were building. And the design was not final, right? Nowhere close. They needed to iterate the design a lot. And they had all these ideas to make all these changes flexibly as the manufacturing process is still going on. And the traditional manufacturer, who they've used for a decade for the last 3 versions, the manufacturer, I won't give the name, but their process is, you have to set up the process, you hit go, and then you build 1,000, right? Like that is what they're optimized for. Build a process, and hit go to make 1,000 bores. You can't stop. You can't make flexible changes, etc. So anyway, they came to tempo, and so this is what they did. So this is what they were used to. What you guys are used to, probably iteration 1, iteration 2. So this is what they did. So they started with the same fab, and then they had multiple assembly batches. And this happens quite often, but the amount of assembly batches that they had for the same fab was quite astonishing. So for the same fab, basically they assembled 10, sent them back the bores. They made some assembly changes, bomb line changes, assembly instruction changes, send us back the changes, build another 10, they made some more changes, etc. So they did that many times for a given fab, because a fab takes many days to fabricate, right? And obviously they were able to get some cost improvements when they got to hit a certain quantity. So they wanted to iterate through the assembly profiles multiple times. And not only that, for each batch, they were making mid-build changes. So they were pushing, as things are going through the pick and place machine, they send us changes. So in effect, what they were doing is they were trying lots of different configurations of the design to meet their reliability and regulatory requirements, and so there's an outcome they were looking for, and they were making all these configurations. So that's sort of the promised land. So recently they started producing production units that they didn't have the time, and so that's sort of the promised land, right? Like high reliability products being built with these type of mid-build changes, and so I think that's really quite powerful. And and obviously digital traceability. Sorry, you can see the text there. Digital traceability and documentation, which is something manufacturers did not like. With continuous manufacturing, this comes for free, right? These are all events that the software is tracking. Who, when, version of customer files used, process input files, materials, customer approvals for process outputs. Many times you want to approve a first article before it moves on, and you want to track that traceability. And then QA approvals. So when you have free digital traceability, what gives that, if you're building a satellite, if you're building a medical device, that gives you a lot of confidence to make changes. So what we're increasingly seeing now, and what will be interesting over the next year, is as you're making these mid-build changes to the factory, you're able to do interesting things for production. So traditionally, this has been a nightmare, but so now that every change is clearly versioned and propagated to factory, you can build a new version of a satellite every 2 weeks, right? Previously, that was like red lights are going everywhere. It's incredibly risky to do that type of thing. But with this type of digital traceability and propagation of changes, you have the confidence to make small changes to satellites and push them out to production every couple of weeks. So that is the promise of continuous manufacturing, and there's still a lot we are learning about what this can enable, and we are learning as we go as well. But it certainly means interesting things for engineers. So that's sort of what I had to talk about for the time I had today. Thank you for your time. But any questions, thoughts? I'm curious to hear any thoughts you have.
Inspection images and thanks. The inspection images and X-ray stuff in the digital traveler that you had, is that part of the standard process now, or is that like a new thing, or I haven't noticed
building
that.
Yeah, so yeah. Building towards it, yeah.
Okay. Awesome.
We'll keep you updated.
Thank you.
Yeah, yeah. There's a version of this that we do that is more manual, but yeah, very very close. Yes, in the back.
What's the one thing you would mostly ask of your designers to, if they could do something better to help your system, what would that be?
Oh man, where do I start?
Pick
Let's see.
one,
I think
two.
I did this talk exactly a year ago. Where do I start? Where do I start? All these stories are going in my head. So I think who uses Gerbers here still? Wow, a lot of you still. All right. Not recommended. There's lots of data that the manufacturing is missing out on when you send Gerbers over. So IPC 2581, ODB++, they're both formats that are much richer with context. We prefer ODB++. We take in native design files, actually. If you're using Altium, you can actually upload a PCB doc directly, and we have a really good export process internally. Man, we wrote articles about this, but so if you want to program the solder paste printer on the floor with high fidelity and quickly, having an ODB++ and having this matrix file that we can export from that is so much easier than starting with Gerbers. And traditionally, it's sort of Gerbers have been the sort of status quo, but there's many quality issues and the speed that you're missing out on, and automated programming that you're missing out on when you're sending Gerbers over. So we're seeing that fall rapidly over the last few years, actually. I would say less than 5% of our customers use Gerbers because that's what that's what their process is. But that should change. Consign parts, man. Like send them on time. It's so interesting. It's like often you find the parts that we're waiting on are the parts from the customer, right? DigiKey and almost never messes up. But any more questions, thoughts? All right, so we're at the 11:45 mark as well. Cool. Well, thank you so much. So let me give you my email. I got a bunch of emails last time I did a talk here. So Shashank@Tempo, if you have any thoughts, questions, ideas for this vision we're proposing. Cool. Thank you so much, guys.